Hello, friends. In the last lecture, we have seen many terminologies which are related to stress-strain relationship. In continuation to that, today we are starting with another terminology, that is strength. Now, in this picture, you can see physical strength as well as a mental strength. So, like I told you yesterday, that is when you try to compare it with the psychological factors, then it becomes easier for you to remember the properties. Now, in this case, if the person is having very good physical strength, then that person will be able to sustain any type of physical trauma. And if he is having good mental strength, then he will be able to sustain all type of emotional trauma without getting disturbed too much or without taking any unwanted step. Now, when it comes to material science, it is the ability of the material to withstand stress without fracture. Now, coming to the flexibility. Now, flexibility, we use this term very commonly. We always say that I'm very flexible. Now, I'm very flexible means either I may be flexible mentally or I may be flexible physically. Now, in case of mental flexibility, that means that I'm ready to adopt to anything. That is, I'm not very stubborn. My thoughts are flexible in nature. When I say physical flexibility means with minimum efforts, I can flex my body or I can bend my body or I can mold my body. So in this picture, you can say this person is able to flex his body anywhere with minimum amount of efforts. So when it comes to material science, it is the maximum strain which is seen in the material when it is stressed not to exceed its proportional limit. Means with minimum amount of stress, the amount of strain which is seen is much more, and it is usually expressed as maximum flexibility, and it is measured as P upon E. What is the clinical significance of flexibility? Now, for example, in case of impression materials, one of the ideal requirements of impression material is that it should have good flexibility. Means when the material is recording the undercut area or the undermining area. So while removing the impression material, in that particular area, the material should flex elastically while removing the impression from the oral cavity. If the material is not enough flexible or it is rigid in nature, then in that cases, while removing, the patient will have too much of discomfort. So one of the requirements for the impression materials that it should have good flexibility. Now, in this case, you can see a root canal instrument having good flexibility, and that's why it is able to bend and reach up to the apex of this curved canal without fracture. Now, the next terminology is resilience. Now, here in this picture, you can see a boy is jumping on this net. Now, whenever he jumps on the net, he falls down and again he is forced up into the air. The same is seen on the trapeze net, which is commonly, we find it in circus. So in that circus, the trapeze, when he falls from those swings onto the net deforms elastically and the energy of his fall gets absorbed by the net. And over a period of time, this energy which has been observed is released and the person is forced into the air and again he falls down. So same thing. If we connect it to the material, then resilience is defined as amount of energy absorbed by the material when it is stressed not to exceed its proportional limit. So it is an energy which is getting absorbed when the material is stretching up to its proportional limit. It is expressed as modulus of resilience R, and the formula is P square upon 2E. Units of measurements are energy per unit volume, that is megajoules per cubic meter or inch pounds per cubic inch. Now, when you see it on the stress strain graph, it is the area below the proportional limit point or the elastic limit point below the stress strain curve. So, resilience. Now, what is the clinical significance of resilience? Now, this is, I can give you the example of a soft liner. Now, the old denture wearer, many a times, they have some trauma due to the faulty denture. Now, in that case, the underlying tissues are traumatized and the patient has come to you for the new denture, isn't it? Because that old denture is giving problem, there is a trauma inside and you have to give a new denture. But the patient is not ready to discontinue the old denture. Now, in this cases, we put soft liners because before recording the new impressions, the underlying tissues has to come to the normal. So whenever you are putting the soft liners, now these soft liners or reliners or tissue conditioners, they're very resilient in nature. Now, what does this resiliency means? Now, here you can see inside the denture, they have put the reliner and this is the edentulous ridge. Now this reliner or the tissue conditioner is very much resilient in nature. So whatever forces are coming on the denture, so they will not be directly going to the edentulous ridge, but they will be absorbed by this resilient material. Okay, so the energy is getting absorbed and then they are slowly released to the underlying edentulous ridge. So whatever traumatized area is there, it won't be exposed directly to the masticatory forces, but it is protected by this resilient material, which is providing a cushioning effect to it. So that is the importance of resilience in dentistry. We can give many more examples. This is one of the classic examples. That's why I've given it here. Now coming to the next property, that is toughness. Again, this is very like commonly used word. I'm very tough. That is, I will not get affected by anything. So basically toughness is defined as the energy required to stress the material to the point of fracture. Okay, so it is the ability of the material to absorb the energy and plastically deform without fracturing. Now, what is this toughness? Basically, it is the amount of energy which is getting absorbed by the material. The material is deforming plastically, but it is not fracturing. So up to that point, whatever amount of energy is getting absorbed or whatever energy required to stress this material, we call it as toughness. Now, if we see on the stress strain graph, that is the complete area beneath that stress strain curve is toughness. That means the material will deform elastically, the material will deform plastically, but it will not fracture. That tough the material is. So here the amount of deformation seen is quite a lot. So toughness depends on the area of plastic deformation, isn't it? Area of plastic deformation. And examples that metals and alloys are quite tough, and these are the units of measurements, that is joules per meter cube or Newton meter per meter cube. Now here you can see the whole area below the stress strain curve is the area of your toughness. Now coming to brittleness. Now brittleness is exactly opposite to toughness. Now it is the property of breaking suddenly with little or no deformation when stressed. Now here the material, whenever you are applying some forces and if the material is brittle in nature, then it will not flex plastically, but it will fracture directly. That is called as a brittle material. So brittle material shows very little or no plastic deformation when they are put into stress. Brittle materials have little deformation before breaking. That was exactly opposite in tough material. Tough materials, they deform plastically, but they never fracture. In case of brittleness, they don't show or they show very little deformation and the fracture. and they absorb very little energy before breaking. Now here is a very clear-cut picture. Now here, one material, one rod is tough and one is brittle. So whenever we are applying pressure, whenever we are applying forces, the tough material will bend, but the brittle material will fracture. So that is the basic difference between the brittleness and toughness. Now coming to the next important property, that is ductility. Now, ductility, whenever we ask the students define ductility, they say it is the ability of the material to be drawn into wire. So, okay, this is okay, but this is not the proper definition. So when you see the definition, it is the ability of the material to withstand permanent deformation without rupture under tensile load. So it is one and the same, but this is a particular definition in by using specific words. So it is the ability of the material to withstand permanent deformation without rupture under tensile load. And it decreases with increase in the temperature. That is nothing but you are able to draw a wire from the metal. Now, the ductility can be measured by three tests, that is percentage elongation after fracture, reduction in the cross-sectional area at the fracture ends, and cold bend test. That is percentage elongation after fracture. Now, in ductility, you're applying tensile types of forces. So whenever you are elongating something, so there is increase in the length. So how much increase in the length is there? That shows the amount of ductility. More the amount of elongation, more is the ductility. Second is the reduction in the cross-sectional area at the fractured end. Now, whenever you are elongating something, although the length is increasing, but it is decreasing in the cross-sectional area. So, after application of the tensile forces, so how much amount of reduction has occurred in the cross-sectional area? That shows the ductility. We have to compare it with the original cross-sectional area and that with the reduction in the cross-sectional area after fracture. Okay, so that is the second way to measure the ductility. And the third way is cold bend test. That is, you have to bend the material over a specified dimension rod. And then after putting it or after drawing it into wire, then again you can bend it. So increase in number of bends, that shows the amount of ductility in the material. Now, next to ductility is malleability. Now, malleability, that is again the same thing. That is, it is able to make into sheets, isn't it? Or hammering into sheets. So what is the exact definition? It is the ability of the material to withstand permanent deformation without rupture under compression. Here the forces are different. There the forces were tensile. Here the forces are compressive forces. And it increases with increase in the temperature. Now, what is the application of this ductility and malleability in dentistry? Now, here you can see the inlay. Now, these metals, if they are ductile and malleable enough, then we can easily adopt the margins properly to avoid the micro leakage. Secondly, you can see the gold pellets. Now, gold pellets are available in very thin sheets, and because gold is the most ductile and malleable metal, you can compact this gold foil into the cavity. Then in the third picture, you can see the platinum foil, which is used in case of ceramic crowns. So platinum foil, again, the adaptation is very good because of its ductility and malleability. So these are the applications in dentistry, that is burnishing of the margins of the restorations. Direct filling gold can be compacted. Very thin platinum foils used in the fabrication of porcelain jacket crowns, or very thin foils which can be used as separating medium. Then orthodontic wires, you can bend the orthodontic wires in any shapes so that we can give required amount of forces over the teeth. So that is the application of ductility and malleability in dentistry. Now, the next property is hardness. Now, hardness, tooth enamel is the hardest structure in the human body, isn't it? So, in metallurgy, it is defined as resistance to indentation, and in mineralogy, it is defined as resistance to scratching. Okay, so it is a resistance offered by the object to indentation or to scratching. That is called as hardness. Now, the resistance offered by the surface of the material to either scratching, abrasion, indentation or penetration, that we call it as hardness, and value of the hardness is expressed in terms of number. Okay, so lower the value, softer the material, and vice versa. Now, importance of hardness in dentistry. Now here you can see a denture, which is made up of acrylic resin. Now here the hardness of acrylic resin is quite low. So if the patient is using any rough material, any rough food while eating or while cleaning the denture, if he is using the coarser type of abrasives, then that will cause scratching of the surface of the denture base because of its low hardness. Now here you can see the cast, which is made up of dye material. Now here the hardness should be good so that while handling the cast or while preparing the wax pattern, uh, the cast or the surface of the cast should not get easily abraded by our sharp instruments. Now this shows the hardness of the teeth. Okay, if the hardness of the teeth, if it is low, of course, the hardness of the teeth enamel is the hardest material, but to unwanted forces or due to some habits or because of using very coarse abrasives while brushing the teeth, it will result into abrasion, that is wearing away of the teeth. Now, especially if you're using, suppose if you're using a crown, the material of the crown, if it is zirconia, the hardness of zirconia is very high as compared to that of hardness of the tooth. Now, in that case, grinding of the opposing tooth can occur due to the high hardness value. Now, here you can see a toothpaste. So, some toothpaste contains more coarser abrasives, which will lead to abrasion of the teeth. So, that is the importance of hardness in dentistry. Now, we will see the measurement of hardness. Now, hardness can be measured by these different methods, that is scratch hardness, indentation hardness, height of elastic rebounds, and penetration method. Now, first we will see the scratch hardness. The name itself is suggesting scratch hardness, that is by scratching one material by the other. Now, usually it is carried out with the help of Mohs scale. Now, what is this Mohs scale? In this scale, all the materials are arranged from the softest material, that is talcum powder or talc, to the hardest material, that is diamond. All the other materials are arranged on the scales according to their hardness value. Now, here scratch hardness means if now talc is soft material and 3 is calcite. So calcite is hard. So talc can get easily scratched by calcite. So in this method, you can just tell the comparative hardness, but no exact hardness value can be seen in this. Only you can tell that this material is harder than this or this material is softer than this. So that is about the scratch hardness, which is usually done with the help of Mohs scale. The next is the indentation hardness, which is very commonly used in dentistry. Indentation means resistance to indentation. So there are 4 different methods. They are divided into 2, that is micro hardness and macro hardness. So under micro hardness comes noob hardness and Vickers hardness. Now noob hardness, it is used for thin plastics, metal sheets, brittle materials, dentine and enamel. Vickers hardness, again, it can be used for tooth structure, then nail casting alloys, brittle materials like ceramics. Then macro hardness, it contains Brinell hardness and Rockwell hardness. Brinell is mainly used for metallic materials in dentistry, and Rockwell hardness is for viscoelastic material. So basically, there are 4 indentation types of hardness tests which are commonly carried out in dentistry. Now, basically, in all the 4, I'll just tell you in short, in all the 4, they have got a indenting tool. Now the indenting tool differ with the method. Now in noob hardness, the indenting tool is a rhomboidal pyramid of a diamond. In case of Vickers hardness, it is square-based diamond pyramid. In case of Brinell hardness, it is a steel ball, and in case of Rockwell hardness, again, it is a conical diamond pointer. Okay, so the tool is different. So what you have to do, that you have to take the test specimen and then you have to press the indenting tool under certain load. and then remove it, and then you get the indentation of that particular indenting tool. And they have provided the formulae for each test. The formula is different. So you have to put the values. In some, you have to measure the depth of the indentation. In some, you have to measure the diameter of that indentation. So accordingly, you have to put the values in the formula and you can calculate the hardness number. Then the next is height of elastic rebound. Mainly it is used for elastic materials. Higher the rebound effect, greater the material hardness. Now here, what has done, from a specified distance, this indenting tool is dropped down on that surface. Now how much it rebounds elastically, that is measured. Okay, so mainly used for elastic materials. So scleroscope is used to measure the height of elastic rebound. So higher the rebounds effect, greater is the hardness of the material. Not commonly used because of the unreliable results. So this is another method to measure the hardness. And the last one is penetration method. Penetration methods is like your measuring of setting time. Similarly, we have some penetration tools here. Now, there are two testers which are used, that is Shore durometer and Barpool tester for composite resins. Now, Shore durometer, we have got two scales, that is Shore A scale and Shore D scale. Now, Shore A scale is used for soft polymers, elastomers, and rubbers. And Shore D scale is used for more rigid polymers, elastomers, and rubbers. Now, here again, they have got two different, the needles have got different dimensions. So what you have to do, take the test specimen and you have to pierce the needle. Now, if the needle is not able to penetrate, that means the material is harder. So how much it can penetrate, that shows you the hardness of the material. So Shore durometer and Barpool tester, they're used to measure the hardness. So there are the four different methods to use the hardness, that is, or to measure the hardness, that is scratch hardness, indentation hardness, then height of elastic rebounds, and penetration method. So this is all about hardness of the material. These are the references of my lecture, and thank you so much for patient hearing.